Hi everyone, is the audio clear? Am I audible? Okay, then let's start. Previous year graph theory questions. Only 19 students have joined so far. Is there any other class going on right now? So let's see this first question. Hopefully you have already attempted all these things. So this is minimum spanning tree question. Actually, this Kruskal algorithm we study in algorithm subject. Okay, so I think algorithm subject is already going on. So is the algorithm subject over in the crash course? Kapil sir is going to teach algorithm subject. Is this over? So in algorithm subject you will study this Kruskal algorithm, minimum spanning tree, Prim's algorithm. These algorithms you will study how to find minimum spanning tree for any graph. These things you will study. Okay, so yeah, so you will study all these things, but let me tell you, basically this minimum spanning tree you will find. So I can give you answer. I will give you right now. I will just directly give you answer, but don't worry about it. So this will be covered in the algorithm subject. Okay, actually this is not part of discrete mathematics syllabus. This is part of algorithm subject. There you will study something called Kruskal algorithm. There you will study something called Prim's algorithm. These two algorithms you will study, and these algorithms are used to find the minimum spanning tree. MST. MST means minimum spanning tree for any graph. For example, for this graph, when you apply this Kruskal algorithm, then what will happen? First you will take this as 2, then you will take this as 3, then you will take this as 4, then you will take this as 5, and then you will take this as 6. So this is how you will you will not take this as 4. Okay, you will not take it. You will not take this as 5, you will take as 4. Basically, okay, what will happen? See, you will take this age, then you will take this age. Okay, so you took this as 2, then you took this as 3, now you will take this as 4. Okay, so you took this as 4. So basically this is like this. Now you cannot take this as 5. You cannot take this as 5 because there will be a cycle. So what you will do, you will take this as 6. So this is the spanning tree that you will get, and the answer will be basically 15. This will be the answer. Okay, so okay, this will be the answer. Yeah. So anyway, this is minimum spanning tree. This is how you can find. This is how you can apply the Kruskal algorithm, and you can apply the Prim's algorithm also. For example, Prim's algorithm, if you start at this vertex, let's assume, then you will first add this as 2. Then now you have added these two vertices. Okay, let's call this vertex A, B, C, D, E. Then what you will do, you will start at vertex A, then you will add this as vertex. You will add this vertex B. Now what you will do, you will add the vertex E. Okay, so after this you will add the vertex D. After that you will so what is the remaining vertex? The remaining vertex is C, so you will add the vertex C. So this is how you will you can get this is how the Prim's algorithm works. This is how the Prim's algorithm works, and basically the answer will be same. Whatever algorithm you apply, the answer will be same. Whether you apply Kruskal algorithm or Prim's algorithm, that is not going to change the answer. The answer will be same. The answer will be 15. Okay, anyway, don't worry, this topic will be discussed in the algorithm subject. Okay, so there you will study this topic. This in the algorithm subject you will study this MST. this Kruskal algorithm, Prim algorithm, you will study these algorithms in the algorithm subject. Let's see, let's move on. So okay, let's see this question. A tree has 2n vertices of degree 1, 3n vertices of degree 2, n vertices of degree 3. Determine number of vertices and edges in the tree. So so how can you solve it? Very easy. First of all, it is a tree, and in tree we have seen one thing, that number of vertices will be equal to, for example, number of vertices is 2n. He has given the number of vertices, so number of vertices will be equal to number of edges plus 1. So this you already know, or you can say that number of edges will be equal to number of vertices minus 1. So this you already know. Number of vertices is 2n, so your number of edges will be 2n minus 1. So this is one equation you can get. Okay, now you can apply the handshaking lemma. What handshaking lemma we have already seen, that sum of degree, sorry, okay, in this question 2n vertices of degree 1. Okay, this is not the complete thing. 2n vertices are of degree 1. Okay, so 2n vertices are of degree 1, 3n vertices are of degree 2, n vertices are of degree 3. So total how many vertices you have? 2n plus 3n plus n. So total 6n vertices you have. So 6n minus 1. So this will be your equation, because total number of vertices you will have is 6n. So number of edges will be 6n minus 1. Okay, so remember here number of vertices is 6n, number of vertices is not n. So the formula that you should apply is number of edges will be 6n minus 1, because number of vertices is 6n. Now you can apply the handshaking lemma. Handshaking lemma says that the sum of degree, what will be the sum of degree? When you sum all the degrees, then what you will get? See, 2n vertices of degree 1. So when you sum all the degrees, then you will get 2n. 3n vertices of degree 2, 3n vertices of degree 2. Similarly, n vertices of degree 3. Okay, this will be equal to twice the number of edges. Okay, so finally what it is, this is nothing but 2n plus, this is 6n plus 3n, that is 9n. So this will be basically 11n is equal to twice the number of edges. Okay, so from here you can see 11n is equal to 2 into what is number of edges? Number of edges is nothing but 6n minus 1. So finally you will get 6n is equal to 12n minus 2. So from here you can see your value of n will be, so okay, some mistake, I think I have made some mistake. This is degree sum formula: 2n vertices of degree 1, 3n vertices of degree 2, n vertices of degree 3. Determine the number of vertices and edges in the tree. In the tree you will have number of edges will be number of vertices minus 1. Number of vertices is 6n, so 6n minus 1, and your degree sum will be 2n plus 2 multiplied by 3n plus 3n is equal to twice the number of edges. This is your 6, and so this is your 11n is equal to twice the number of edges. 11n is equal to twice the number of edges is 6n minus 1, 11n, so this will be 12n. So from here what you will get? You will get n equal to 2. So yes, so your n will be 2. So if your n is equal to 2, yes, it is correct. So n is equal to 2. Number of vertices is 6n, means number of vertices will be 12. So number of vertices will be 12. So the answer will be this, because number of vertices will be 12. So number of edges will be 11. Yes. So this is correct. So in this question we have used only two concepts. The first concept is that in any tree the number of edges will be equal to number of vertices minus 1. So this is one concept, because in tree number of edges will be number of vertices minus 1. And the second concept that we have used is degree sum. So this handshaking lemma. So we have already seen what is handshaking lemma. So these two concepts we have used, and from these two concepts we can find the value of n. Value of n will be 2, but remember answer will not be 2, because the value of n is 2 and the number of vertices is 6n. So number of vertices will be 6 into 2, that is 12. Okay. So if anyone has any doubt, then you can ask. Now this is the question. He is asking clique. Clique in undirected graph. What is the clique? So let me tell you. So we have already seen what is the subgraph of a graph. I told you, for example, if you have a graph like this, let's assume A, B, C, D, let's assume this is your graph. Then for this graph, if you remove vertices or if you remove edges, then you will get subgraph. This we have already seen. You can remove 0 or more number of vertices, or you can remove 0 or more number of edges, or you can remove both vertices and edges. Basically, if you remove edges, if you remove vertices, then you will get subgraph. Now, what is a clique? What is a clique? Clique is nothing but a subgraph which is complete graph. So basically, clique is nothing but a subgraph which is complete graph. Or I can say basically clique is nothing but complete subgraph. You already know what is complete graph. Complete graph means you have all the vertices are connected. That is your complete graph. So for example, if you have this is your graph. Let's assume this is your graph. Then you can see this A, C, D. This is a clique. Why this is a clique? Because you can see this ACD is a clique because first of all this is a complete graph. First of all this is a subgraph and this is complete graph. Means this is a subgraph and this is a complete graph. So this is a clique. Okay. For example, this is not a clique. Remember, this is not a clique. Why? Because this is subgraph, but it is not complete. Okay, it is a subgraph. Yes, it is a subgraph, but it is not complete. You can see it is not complete because this A and D are not connected, B and C are not connected. So it is not complete. It is subgraph, but it is not complete. Okay. For example, okay, let's take one more example. So let's assume you have this example. You have this A, B, C, D. So if for this graph, for this graph G, let's assume this is your graph G, then remember G itself is a clique because this G is a subgraph of itself. So this G is I told you every graph is a subgraph of itself. Okay, so this G is subgraph of itself. So yes, subgraph. Okay, it is a subgraph of itself and it is also complete. So remember, this G itself is a clique, but of course you can have other clique also. For example, this A, C, D, this is also a clique. For example, this B, D, C, this is also a clique. Okay, remember this C, D, this is also clique. This is also clique. Why? Because you can see this is a subgraph. First of all, this edge CD, this is a subgraph. Also, this is complete graph. You can see this CD, this is a complete graph on two vertices. So this is a complete graph, this is a subgraph. So basically, clique is nothing but subgraph and complete graph. So basically complete subgraph. Okay. So now let's see this question. So basically he is saying that clique in an undirected graph is a subset V of vertices, such that every pair of vertices is connected by an edge, because it must be complete. So basically it must be complete. Every pair of vertices in V dash is connected by an edge. So that this will be your answer. Okay. So induced subgraph may be the same property applicable होती है. See, induced subgraph is a different thing, because for example, take this example, A, B, C, D. Take this example. This is your G. Then in this G, if you see, this is also induced subgraph. For example, if you take induced subgraph on A, B, C, then this will be your induced subgraph. This is your induced subgraph, because in induced subgraph you can delete vertices. You cannot delete edges, but you can delete vertices. So you can delete this vertex C. So you will see that this is induced subgraph, but you can see this is not clique. So this is induced subgraph. Okay, this is induced subgraph. So this is induced subgraph, but it is not a clique. Okay, it is not a clique. So are you getting my point? And the point is that this clique is nothing but a subgraph which is complete. Okay, which is complete. So that's why we can say the answer will be option 3. a subgraph in which every pair of vertices is connected by an edge, means complete. Okay. So this induced subgraph and this clique, these are two different concepts. Okay. Now let's see this question number 4. Suppose that a connected planar graph has 6 vertices. So this is a connected planar graph, and in this we have 6 vertices and each of degree 4. How many regions are there? So he is asking number of regions. So you know, for any connected planar graph, for any connected planar graph, we have Euler formula. Euler formula. It says that number of regions is equal to E minus V plus 2, means number of edges minus number of vertices plus 2. So he is asking what is R. He has given he has given 6 vertices are there. Number of edges we need to find. So to find number of edges, we can apply the handshaking lemma. Handshaking lemma says that summation of all degrees. What is the summation of all degrees? There are 6 vertices, each of degree 4. So this is summation of all degrees. This will be equal to twice the number of edges. So from here the number of edges will be your 12. So this will be your number of edges. So finally number of regions will be, this is number of edges minus number of vertices plus 2. This the answer, you can see the answer will be 8. So answer will be 8. So just very simple, just apply the Euler formula. For connected planar graph we have this Euler formula. We have seen this thing, this formula we have seen already. So the answer will be 8, because he is asking number of regions. Next, for which value of m and n does the complete bipartite graph have a Hamiltonian circuit? We already know what is Hamiltonian circuit. Hamiltonian circuit means basically you start at some vertex. Let's assume you start at some vertex A. Then you visit each vertex exactly once. Remember, each vertex exactly once, and then you come back to vertex A. This type of cycle is called Hamiltonian circuit. This type of cycle is called Hamiltonian cycle, or you can say Hamiltonian circuit. So now he is asking for which value of m and n does complete bipartite graph has Hamiltonian circuit. See, let's assume that you have a complete bipartite graph in which the number of here this m is, let's assume 2, and the n is equal to 1. Let's assume basically m is not equal to n. Let's assume. So take this situation. So you have 2 vertices here and 1 vertex here. Now, so this, because this is a complete bipartite graph, so this graph is like this. Now this is your graph. You can see in this graph we do not have Hamiltonian circuit. Why? Because you can see that, for example, if you start at any vertex you can take any vertex. If you start at vertex A, for example, if you start at vertex A, then you can go here, then you can go here, but now you cannot come back to A. So you can see that when m is not equal to n, okay, then Hamiltonian circuit cannot exist. Okay, let's take one more example. For example, let's assume you have 2 vertices here, A, B, and let's assume there are 3 vertices here, 1, 2, 3. But because it is a complete bipartite graph, so you have these type of edges. Because it is a complete bipartite graph, so you have these type of edges. So this is the edges that you will have. Okay, now for this graph you can see there is no Hamiltonian circuit. Why? Because you can start at any vertex. Okay, whichever vertex you try. For example, let's assume you start at vertex 1. If you start at vertex 1, okay, let's assume you start at vertex 1. Now from 1 you can go to A. So you can, from 1 you can go to A. From A you can go to, let's assume 2. From 2 you can go to B. From B you can go to 3. Now from 3 you cannot go to 1. Why? Because from 3 if you want to go to 1, then you will have to revisit A or B. But in Hamiltonian circuit we visit each vertex exactly once. So you can see that from vertex 3 you cannot go back to vertex 1. Okay, so that's why we can say that there is no Hamiltonian circuit. Remember here m is equal to 2, n is equal to 3. So basically when m is not equal to 2, when this situation happens, when m is not equal to when m is when m is not equal to n, when this situation happens, when m is not equal to n, then you can see that there is no Hamiltonian circuit. There is no Hamiltonian circuit. Remember, there is Hamiltonian path. This is Hamiltonian path. So this is Hamiltonian path, but this is not Hamiltonian circuit. Hamiltonian circuit means Hamiltonian cycle. So there is no Hamiltonian cycle when you have m equal to when you have m not equal to n, then there is no Hamiltonian circuit. Okay. So and also when you have m equal to n, then when both are basically m equal to n and both are greater than equal to 2, then you will have Hamiltonian circuit. For example, take this a b 1 2. Okay, because this is a complete graph, so you will have this type of situation. Now you can see in this graph, you can see that there is Hamiltonian circuit. How? You can start at vertex a. From vertex a you can go to 1, from 1 you can go to b, from b you can go to 2, and now from 2 you can go to 1, because from 2 you can go to from 2 you can go to a. So you can go like this. So from 2 you can go to a. So this is Hamiltonian circuit. So you can see that Hamiltonian circuit will be there when m equal to n. So what I can say like this: when m equal to n and both are greater than equal to 2. Remember why? Because if both are 1, let's assume both are 1, you have one vertex here, one vertex here, then there is no Hamiltonian circuit. Okay, then there is no Hamiltonian circuit. Why? Because you can see if you start here, then from a you can go to 1. Now you cannot come back to so now you cannot wait a second. So when you have this type of situation, so from a you can go to 1, and so this, okay, so this is not a Hamiltonian circuit, because this is not a cycle itself. You can see one thing, this is not a cycle. Cycle starts with 3 vertices. At least 3 vertices you need to have a cycle. So you can see when you have m equal to n equal to 1, then you do not have Hamiltonian circuit, because there is no cycle itself. To have a cycle you need at least 3 vertices. Okay, so that's why we can say that when m equal to n and both are greater than equal to 2, okay, then Hamiltonian circuit will exist. When m is not equal to n, then Hamiltonian circuit will not exist. So answer will be option 3 and option 4, both are correct. Option 3, option 4, both are correct, but option 3 is better answer, because option 3 will cover option 4 also. You can see option 3 is covering option 4. Actually option 3 and option 4 both are correct. Okay, option 4 is not incorrect, option 4 is also correct. So option 3 is correct, option 4 is correct, and when 2 options are correct, then you should select better option. So better option will be option 3, because option 3 will cover option 4 also. You can see option 3 will cover option 4 also. So that's why. So answer will be option 3. Let's see this. What is this? Again the Kruskal algorithm is there, minimum spanning tree, Kruskal algorithm, and he is asking so this Kruskal algorithm you will study in the algorithm subject. So don't worry here, you don't have to worry about this Kruskal algorithm, this MST question in discrete mathematics, because in algorithm subject you will study this Kruskal algorithm, Prim algorithm. So you can solve this question there. Okay, so there is no need to solve this question right here. Okay, so he is saying that using Kruskal algorithm to find the minimum spanning tree of the graph, the weight of the spanning tree is. So he is asking this question. Anyway, you can solve this question very easily. So solving this question you can very easily solve by Kruskal algorithm. What you can do, you can take this edge. First you can take this edge, then you can take this edge. So these 2 edges you can take. So now after that, so basically you have taken this is your word. So you have taken this edge. Now you can take this edge also. So you can take the, let me name all these vertices. Let me name these vertices: A, B, C, D, E, F, G, H and I. So these are our vertices. How many vertices are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 9 vertices are there. So now what you will do, first you will take this edge, because this is minimum edge, so you will take this edge. Then you will take this edge, so this is your G to I, G to I, so this edge also you will take. Then you will take this F to E, F to E, this edge also you will take. So all these 1 edges we have taken. Okay, now you can take this edge, this edge to A to H, this edge also you can take. Okay, A to H, this edge also you can take. Now you can take this G to F, so this edge also you can take. G to F, this edge you can take. So this G to F. Now what is the, for example, A to I, A to I, this edge you can take. So A to, sorry, A to I, wait a second. Wait a second, A to I. Okay, so from A to I, this edge you can take, and then you can take B to I. So B to I you cannot take, this you cannot take because there will be cycle. So what is the edge that is remaining? So we have taken all the 2 edges, and so now you can take the 3 edges. For example, B to C you can take, B to C you can take, and actually because there are how many vertices are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 vertices are there, so you need 8 edges. Have we gotten 8 edges? 1, 2, 3, 4, 5, 6, 7. One more edge is required. So which edge? So this vertex D we have not covered, so we can cover this vertex D with I to D. So this is how we can cover. So this is your minimum spanning tree. Okay, so anyway, you can just now you can find the answer will be 1 plus 2, that is 3, 3 plus 3 is 6, 6 plus 4 10, 11, 12, 13, 14, and this is 16. So the answer will be 16. Okay, so anyway, don't worry about this question. I have just solved it for the sake of completeness. I solved it, so the answer will be 16. Okay, so the answer will be 16. But don't worry about this question. In algorithm subject, you will study this Kruskal algorithm, Prim's algorithm. You will study in the algorithm subject. So do not worry about this question right here. Okay. Now, okay. So Sharda is saying clique is not clear. So clique is nothing but a complete subgraph. Okay. Let me tell you again. If you have, let's assume you have this graph. Let's assume this is your graph. Let's assume this is your graph, A, B, C, D, E, F, G, H. Let's assume this is your graph. Okay, in this graph you can see this edge CD, this is clique, this edge CD, this is clique. Why? Because this edge is subgraph. First of all, this edge is subgraph, and also this edge is complete graph on 2 vertices. So this is a clique. For example, you can take any edge. You can take any edge that is a clique. Okay, this is also a clique because this is subgraph and also it is complete. Okay, so for this graph you can see all these things are clique. Remember, this thing is not clique. A, B, G, H. This is not clique. This is a subgraph. This is a induced subgraph. First of all, this is a induced subgraph. Okay, so this is the induced subgraph, but this is not a clique because it is not complete graph. This is not a complete graph, so it is not clique. Okay, clique means a subgraph which is complete graph. A subgraph which is complete graph. So your subgraph must be complete graph. That is the definition of clique. Okay, so you can see this is induced subgraph, but it is not complete. But it is not complete graph, and hence we can say this is not a clique. Okay, so this is not a clique. So this is a simple definition of clique. Is it clear? So let's see this question. This question is like there are two theorems are there. One is Dirac's theorem and another is Or's theorem. So we have two theorem. Okay, so I will share the link on our group. I will share the link. So there are two theorems. There is Dirac theorem and there is Or's theorem. So these two theorems we have. Okay, these two theorems we have. So these theorems are beyond our we did not see these theorems, but I will share the link. Okay, so you can solve this question using these two theorems, and the answer actually will be among these, the answer will be this third. So this is correct. Answer will be this statement is true and these statements are false. Okay, anyway, don't worry about this question. What I will do, I will share these two theorems I will share. Okay, so one is Dirac theorem. Okay, one is Dirac or whatever, Dirac, whatever. So Dirac's theorem. Okay, and another is Or's theorem. These two theorems we have about Hamiltonian circuit. So we have these two theorems. Okay, about Hamiltonian circuits. We have these two theorems. These two theorems I will share, and I will share the link of these two theorems. Okay, so after just these are two statements, and after studying these two statements you can solve this question and the answer will be D. Anyway, there is nothing interesting in this question, just two theorems we have, and I will share the link in our WhatsApp group. I will share the link and you can just read the statement of Dirac theorem. Also you can read the statement of Or's theorem. Okay, so okay, Khushbu, you can check the Dirac's theorem. Okay, just check the Dirac's theorem and you can solve this question. Okay, right now actually I am not focusing on this Dirac theorem or Or's theorem because it's not interesting. Like in GATE exam they will not ask you this type of question. I don't know why in UGC exam they are they are so interested in these two theorems. Anyway, so let's do one thing. I will share the Dirac theorem, Or's theorem, and we can solve this question after reading the statement of these theorems. Okay, so you can skip this question, right? For now you can skip this question. Also you can skip this. Was also same question, same Dirac's theorem and Or's theorem we need here. In this question also we need Dirac and Or's theorem. Okay, so okay, so this is also about Hamiltonian graph, and again in this question also, yes, in this question also we use the Dirac's theorem, Or's theorem, the same thing. I think in UGC NET they have asked this question 3 or 4 times. This same question 3 or 4 times they have asked. So this from UGC point of view, this Dirac theorem, this Or's theorem, these two theorems are important from UGC point of view. Okay, so just read the statement of these two theorems. Okay, just read the statement of these two theorems and you can solve the questions. Okay, you can answer the questions. From GATE point of view it is not important. Okay, anyway, so again the same question, same Dirac and Or's theorem. You can see 3 or 4 times they have asked the same question. They are just copying their own question. They are copying every year and they are asking. So anyway, let's see this question. This is again minimum spanning tree question. So I will not focus on this question here. Okay, you can solve this question when you study in algorithm. So in algorithm subject you will study this minimum spanning tree problem. You will study Kruskal algorithm. You will study this Prim's algorithm, and there you can solve this question. So I won't be spending time here because again in algorithm subject Kapil sir is going to teach you this question again. So they are going to solve this question. So let's not waste waste time on this question, because anyway this question will be solved by Kapil sir. Okay, you can very easily solve this question actually. Just make the graph and just find this minimum spanning tree. So see in this question, okay, let me just tell you the graph. Let me tell you the graph. What is the graph? See, it is saying that you have a graph in which number of vertices are greater than 2 and you have these vertices. So there is vertex v1, v2, v3, v4. These are the vertices that you have, vn. These are the vertices that you have. Now he is saying that two vertices vi, vj are connected if and only if I minus j should be greater than 0, less than equal to 2. So for example, v1 is connected to v2. Why? Because 1 minus 2 this is saying that this I minus j, this should the I minus j, this should be less than or equal to 2. So you can see 1 minus 2. 1 minus 2 is you can see 1. This is modulus operation actually. So 1 minus 2, this will be minus 1, and this again will be 1, because this operator makes everything positive. For example, this will be 5. Okay, it makes everything positive. So finally this v1 is connected to v2, this v1 is connected to v3 also. Why? Because 1 minus 3 is equal to 2. So that's why this v1 is connected to v3 also. Remember, v1 is not connected to v4 because 1 minus 4 is equal to 3. So 3 is not less than equal to 2. So that's why v1 is not connected to v4, v1 is not connected to v5. We can say that v1 is connected to v2, v1 is connected to v3. Now v2 is connected to v3, v2 is connected to v4, v3 is connected to v4, v4 is connected to v5, and so on. So this is how this graph is, this is how the graph we have. Okay. Now in the question he is saying that so each edge is assigned a weight of I plus j. For example, the weight of this edge, for example, the weight of this edge is 3, the weight of this edge is 5, the weight of this edge is 7, the weight of this edge is 4, the weight of this edge is 6, and so on, because every edge has a weight I plus j. Okay, so for example, this edge between v2 and v4, this edge will have the weight 2 plus 4, that is 6. So now if you want to find the minimum spanning tree, then what you will do, you can take this you can take this v1 to v2, you can take this edge 3. Okay, then you can take this edge 4 and you can connect v3. So you can take this edge 4. Now what you can do, you can take so you have connected this v1, v2, v3. Now what you can do, you can connect this v4, you can connect now. How can you connect this v4? So to connect this v4, you can take this edge 6. So this edge 6 you can take. So from v2 to, so this edge 6 you can take. Now you can connect v5 also. So to connect v5, you can take this edge 7. So finally this is how you can construct the minimum spanning tree. Okay, so anyway, this is how you will get the graph, and this is how you can construct the minimum spanning tree. So I won't be spending time in this question. Okay, let me tell you how to solve this question for 4 number of vertices. You can try this question afterwards. If you have 4 vertices only, then it is very easy. For example, this edge has this edge will have weight 3, this will have 5, this will have 7. Now this is having 4, and this is having 6. So this is your graph. When you have 4 vertices, then this will be your graph. Now what you can do, you can take this minimum spanning tree. How can you find minimum spanning tree? You can take this v1 and you can connect, this will be your v2. Okay, now so then after from once you have connected this v2, then you can take this edge 4 and you can connect v3. Then you can take this edge 6 and you can connect v4. So your answer basically will be 6 plus 4 plus 3. If you have 4 vertices, then your answer will be 13. Anyway, your you can just find your answer. Okay, so for 10 vertices you can try and you can find this answer. But anyway, actually I am not focusing on this question right now, because you will study this minimum spanning tree questions. You will solve this same question again in the algorithm subject. Okay, so let's see again the same Kruskal algorithm. So let's skip this question because you can solve this question in the algorithm subject. Okay, so next again minimum spanning tree question. So again I am skipping this question because in algorithm subject you can solve this question. So that's why I am skipping this question. Okay, in algorithm subject Kapil sir will solve this question. Okay, and this again the same question, that Dirac theorem, the same thing, the Dirac theorem and OR theorem. So the same question. I told you that in UGC NET almost 4 times they have asked this same question. So this Dirac theorem, OR theorem, I think I don't know why they are so obsessed about these theorems. So this is important. These two theorems, Dirac theorem or theorem, these two theorems are important from UGC point of view. Okay. So these two theorems I will share today in our WhatsApp group. I will share the link to these two theorems. You can read the statement of these two theorems. Okay. Now let's see this question. Euler circuit. So we have already seen that this theorem we have already seen that in a connected graph we have Euler circuit. G has Euler circuit if and only if all vertices are of even degree. All vertices are of even degree. Right? This we have already seen. A connected graph. A connected graph has Euler circuit if and only if all vertices are of even degree. So in this question, all you need to do is just find the degree of the vertices. For example, the degree of this vertex B. What will be the degree of vertex B? The degree of vertex B is 3, because you can see there are three edges that are incident on vertex B. So the degree of B is 3. The degree of A is 3. The degree of E is 3. The degree of D is 2. The degree of C is 3. So you can see in this graph G1 we do not have Euler circuit, because a graph has Euler circuit if and only if. So yeah. So what I'm saying a graph has Euler circuit if and only if all the vertices are of even degree. But in this graph you can see, in this graph G1 you can see this vertex A, vertex E, vertex B, vertex C, they have odd degree. So this graph does not have Euler circuit. Let's see this graph. This D has degree 3. So again, because this D has degree 3, so you don't even need to find the degree of other vertices, because you can see because this does not have Euler circuit. So both of them do not have Euler circuit. Okay, because you can see this vertex D has odd degree, and that's why this graph G2 has no Euler circuit. Okay, so let's see this again, the same type of question. Okay, he is asking you have n number of vertices, then what will be the answer? You see this question, you can very easily solve this question. Take n equal to 3. Take n equal to 3, then you will have v1, v2, v3. Take n equal to 3. See, then what you will have? You will have v1, v2, v3. 3 vertices you will have. Okay, now he is saying such that weight of edge vi, vj is 4. So the weight of this edge v1, v2. What is this? 4 into 1. So this is 4. Now what is this? This is again 4. And what is this? This is 8. So now you can find the minimum spanning tree. The minimum spanning tree will be simply v1, v2, v3, 4, 4, and the answer will be you can see the cost, the total will be 8. So actually when you put n equal to 3, then the answer should be 8. Just see which option is correct. This option is not correct. This option is not correct. Let's see, this option is not correct. Let's see this. So this option is correct. So the answer will be option 3. So this is how you can solve this question. Very easily you can solve this question. Just take n equal to 3 and you can solve this question. Okay. Anyway, this MST question, minimum spanning tree question, this you will again see in the algorithm subject. Let's see this question. How many different spanning tree are there in a complete graph on 4 vertices in a bipartite graph? So it is we have a formula, we have a direct formula. If you have a complete graph on n vertices, then the number of spanning trees will be n power n minus 2. Okay, so if you have a complete graph on n vertices, then this will be our number of spanning trees. If you have a complete bipartite graph, this is complete bipartite graph, then number of spanning tree will be m power n minus 1 multiplied by n power m minus 1. So this is a formula we have. Okay, so again these things also you will study in the algorithm subject. But anyway, this is just direct formula that we have. In complete graph on n vertices, this is the number of spanning tree we will have. N equal to, sorry, number of spanning tree will be n power n minus 2. And in complete bipartite graph, this will be your answer, m power n minus 1, n power m minus 1. So the answer, what will be the answer here? Because this is k4, so the answer will be 4 power 4 minus 2. This is nothing but 4 power 2, that is nothing but 16. Okay, so now for this what will happen? 2 power 2 minus 1, 2 power 2 minus 1. So the answer will be 2 into 2, that is equal to 4. So the answer will be 16 comma 4. Answer will be option 3. Okay. Anyone has any doubt, then you can ask. Okay, so let's see this question. In this question, remember in this question he has changed the definition of clique. Basically in this question he is saying that a clique is a complete subgraph that is not contained in any larger complete subgraph. What he is saying, basically in this question, the clique, by clique he means maximal clique. By clique he means maximal clique. Actually, okay, let's see. When we took this example, A, B, C, D, earlier when we took this example, then I told you that this edge AB is a clique. I told you this thing. This edge AB is a clique. I told you this thing. But this edge AB is not a maximal clique. This is not a maximal clique. Why? Because you see this is also clique. This is also clique. Okay. You can see this edge AB is contained in this clique. See, this is also clique, this is also clique. Okay, this is clique, this is clique. But this clique is contained in this clique. This clique is contained in this clique. So this is not maximal clique. This is not maximal clique. Maximal clique, what it means? Maximal clique means a clique which is not contained within another clique. For example, take this example. In this example you can see A, B, C, D. Then remember AB is a clique. AB is a clique. Okay, yes, AB is a, wait a second. Yeah, so this AB is a clique. Just give me a minute. Wait a second. So what I'm saying, yes. So in this graph you can see this AB is a clique. Okay, this AB. Wait a second. Some issue with the tablet. There is some issue with my tablet, so let me check it. You can ask your doubt. If anyone has any doubt, you can ask. So what I'm saying, yes, I'm saying that this AB is a clique, okay, because this is a complete subgraph. You can see this is a complete subgraph. Now this DC is also clique. This DC is also clique because this is also complete subgraph. Remember this ADC, this is also clique because this is also complete subgraph. Okay. Remember this is not a maximal clique. This is not a maximal clique. Why? Because this AB, this AB is contained within another clique. See, this is also a clique. This ABC, this is also a clique. Okay, this ABC, this is also a clique. So you can see that this is AB is contained within this clique. So that's why this is not maximal clique. This is not maximal clique. This is maximal clique. This is maximal clique. Okay, are you getting my point? So let's take one more example, one last example. Let's take so A, B, C, D. In this example, you can see this this ADC. This is a clique. This is a clique. Yes, this is a clique because it is a complete subgraph. Okay, but remember this is not a maximal clique. This is not a maximal clique. This is not a maximal clique. Why this is not a maximal clique? Because we have another clique which contains this clique. So you can see this is a clique, this is a clique, and you can see this clique is contained within this clique. So that's why we can say this is not maximal clique, this is maximal clique. So this is how you can find clique or maximal clique. But if you see in this question, they have done something. In this question, they have defined the clique to be a complete subgraph that is not contained in any larger complete subgraph. Basically, in this question, they have defined the clique to be maximal clique. So remember, in this question, by clique, they mean maximal clique. Remember this thing. Okay, in this question, by clique, by the word clique, they mean the maximal clique. Now let's find what will be the maximal clique in this graph. So in this graph, very easily you can find the maximal clique. See, this is maximal clique. This is this BCEF. This BCEF. Okay, this is maximal clique. You can see. So this is a maximal clique. You can see this is this thing. Okay, this BCFE. So you can see this is a maximal clique. Okay, so this is one maximal clique that we got. Remember this A, B, G, E, D. This is not a maximal clique. Remember, this is not a maximal clique. First of all, this is not a clique. Why? Because this is not a complete graph. Because remember, this is graph on 5 vertices A, G, B, E, D. So there are 5 vertices in this graph. Okay, so this A, B, G, E, D, this is not a maximal clique. Okay, this is not a maximal clique. So, but this is a maximal clique. This A, G, D. So remember this A, G, D means this A, this G, this D. This is a maximal clique. Similarly, this A, B, G, this is also maximal clique. This A, B, G, this is also maximal clique. Similarly, this D, G, D, G, E, D, G, E, this is also maximal clique. Similarly, B, G, E, B, G, E, this is also maximal clique. So you can see total 5 clique we have. Total 5 maximal clique we have. And he is asking how many maximal clique we have. So the answer will be 5. So remember, this B, E, C, F, this is maximal clique. B, C, E, F, this is maximal clique. A, G, D, this is maximal clique. A, B, G, this is maximal clique. D, G, E, this is maximal clique. And B, G, E, this is maximal clique. So these 5 maximal clique we have. So the answer will be 5. Let's see this question. In this question, what he is saying, a connected multigraph has Euler circuit if and only if each of its vertices have even degree. So this is correct. So this is true statement, but remember he is asking false. Remember this thing. So this is a true statement, but he is asking false. This we already know. Now next, A connected multigraph has Euler path but not Euler circuit if and only if it has exactly two vertices of odd degree. This is also correct. This statement is also true statement. Okay. Next, a complete graph has a Hamiltonian circuit whenever n is greater than equal to 3. So this is also correct. Why? Because you see, a complete graph on 3 vertices you can take A, B, C. This complete graph on 3 vertices has Hamiltonian circuit. You can start from A, then you can go to C, then you can go to B, then you can go to A. So this is a Hamiltonian circuit that you have. Similarly, if you have complete graph on 4 vertices A, B, C, D, if you have complete graph on 4 vertices A, B, C, D, then you can have Hamiltonian circuit very easily. A to B you can go, B to C you can go, C to D you can go, and D to A you can go. So this is your Hamiltonian circuit. So you can see that complete graph has Hamiltonian circuit whenever n is greater than equal to 3. So this is also correct. This is also true statement. What is the last statement? A cycle over 6 vertices is not a bipartite graph, but a complete graph over 3 vertices is bipartite. So what is he saying? In the last option he is saying that C6 is not bipartite graph. So let's see what is C6. C6 is this A, B, C, D, E, 1, 2, 3, 4, 5, F. This is your C6. This is your C6. We have already seen this graph, cycle graph. We have already seen in our lectures. What is cycle graph? This is your cycle graph. Let's see whether it is a bipartite graph or not. See what you do. Let's try to make it bipartite. Let's try to make it bipartite. So you take A and you put it here. Now you cannot put B here, so you will have to put B here. Now where can you put C? You will have to put C here because B is connected to C, so you cannot. So this is your partition 1. This is your partition 2. So this C you cannot put in the partition 2. You will have to put this C in partition 1. Where can you put this? Where can you put this D? So this D you will have to put here. Where can you put this E? You will have to put it here. Where can you put F? You can put it here. So this is how you can find the partition. You can see. So this is actually a bipartite graph. So C6 is a bipartite graph. Now in the next statement he is saying that complete graph over 3 vertices is bipartite. Complete graph on 3 vertices. This is not bipartite because, for example, A, B, C, let's assume. Now try to make it bipartite. Then let's assume you put A here. Let's assume this is partition 1, partition 2. So let's assume you put A in the partition 1. Now you cannot put B in the partition 1. You will have to put B in partition 2. Now where to put C? You cannot put C in partition 1. You cannot put C in partition 2. So that's why you can say that this is not a this is not a bipartite graph. So that's why answer will be only D. So answer will be 4, only D. So first 3 statements are true statements and he is asking false statements. So the answer will be D. Cycle graph with even number of vertices are always bipartite. Yes, cycle graph with even number of vertices is always bipartite. Yes, okay. And also cycle graph with odd number of vertices is never bipartite. Okay. So we have seen that C6 is bipartite, C3 is not bipartite. Okay. Similarly, you can see that this C5 is not bipartite, C8 is bipartite. Basically, cycle graph on even number of vertices is bipartite, cycle graph on odd number of vertices is not bipartite. Okay. So let's see this question. He is saying that the two distinct set of vertices which makes the graph bipartite. So let's see. Okay. Now, so let's check each option. Okay, just check each option. Okay, there is nothing, just check each option. For example, in first option he is saying v1, v4, v6, v1, v4 and v6. Okay, so basically he is taking and he is saying v2, v3, v5, v7, v8. Okay, so basically see v2, v6. Okay, he is saying v2, v3, v5, v7. So you can see this is not correct. Why? Because there is edge between v3 and v7, so that's why this is not correct. So option 1 is not correct. Okay, wait a second. So option 1 is not correct. Okay, option 1 is not correct. Let's see option 2. In option 2, what he is saying, in option 2 he is saying that total 7 vertices you have in option 2 and total 8 vertices are there, v1, v2, v3, v4, v5, v6, v7, v8. So you can see this option 2 is also not correct, because the total number of vertices is itself is 7. The total number of vertices should be 8. You can see the total number of vertices should be 8, but in option 2 the total number of vertices is 7. Okay, so that's why, okay, that's why this option 2 is not correct. Let's see option 4. This option 4, let's see. So v1, let's see this, v2, v3, v5. So v2, v3, v5, this is okay. Let's see v1, v4, v6. So what is saying, v1, v4, okay, v6, v7, v8. Now this is here, so you can see this v8, v4, this v8 and v4, they have edge, so that's why this is also not correct. So the answer will be option 3. So this is how you can check. Remember, in bipartite graph what happens, you have partition 1, you have partition 2. First of all vertices must be covered, means some vertices you have here, some vertices you have here, but you must cover all the vertices. This option 2 is not covering all the vertices. This option 2 is not covering all the vertices. You must cover all the vertices. So that's why you can see this option 2 is not correct. Okay, this option 3 is correct. Okay. Next, what is this? A tree with n vertices is called graceful if its vertices are labeled with integers 1 to n such that the absolute value of difference of the labels of adjacent vertices are all different. Which of the following trees are graceful? So he is saying that, see, a tree is graceful if its vertices are labeled from 1 to n, okay, so that absolute value of difference of labels of adjacent vertices are all different. So see, this is not graceful. This first is not graceful, because if you see v1, v2, v3, v4, then the difference here is 1. The difference here is 1. Okay, the difference here is also 1. So that's why this is not graceful. Okay, am I reading it correctly? He is saying that so that the absolute value of the difference of the labels of adjacent vertices are all different. If its vertices can be labeled so that the absolute value of difference of labels of adjacent vertices are all different. So I think this is not a grace. Okay, wait a second. I think this is not how, okay, this is not what it wants to say. What it wants to say, what does it want to say? What is the meaning of this question? I think this is not what it wants to say. So okay, maybe he wants to say that for each vertex, okay, maybe he wants to say that for each vertex, for example, for this vertex, okay, because this is a 1 degree vertex, you don't have to check. Let's check for this vertex. For this vertex, this difference is 1, this difference is also 1. So this is not a grace, this is not graceful. Okay, let's check this option B. In this option B, what he is saying, v1, v2 with this, and v4, v5. So you can see this is also okay, let's see this, v1, v2, v4, v5, v3. See, you don't have to check v1 because it has only 1 degree. You can see this difference is 1, this difference is 2, this difference is 1. Okay, so this is also not graceful. This is also not graceful. Are all different. So this is also not graceful. So none is graceful. we can label it in another way also. Okay, a tree with n vertices is called graceful if its vertices can be labeled with integers. Okay. I did not understand this question. He is saying can be labeled. Can we label it? For example, v1, v2, v3, v4. Can we label it? For example, let's label it 1. Okay, now give it label 3. So can we label it with difference? The difference must be all different. So if you see this, then this will be basically the difference will be 2. So you can take 4 here and you can take 2 here, or you can take 4 here, then you can take 3. Okay, I'll check this question. Okay, I'll check this question and I'll answer it. I'll answer it afterwards. Okay, I'll check this question. Okay, for now, let's skip it. I will check it and I will answer it afterwards. Okay. So this same question again, the same question. You can see this is the 5th time. So I think you must, from UGC point of view, I don't know why they are so obsessed about this question. Again this Dirac theorem, again this OR theorem. So this same question has come for the 5th time. Okay, so okay, just give me a minute. I'm connecting my laptop to the charger. Okay, so what is the next question? Let's see. Given again the minimum spanning tree. So let's skip this question right now, because in algorithm subject you are going to study this question again. Okay, so there is no point in spending double time. So let's see this. This question. A certain tree has 2 vertices of degree 4. So you see 2 vertices are of degree 4 and 1 vertex of degree 3 and 1 vertex of degree 2. Okay, if the other vertices have degree 1, let's assume there are k other vertices, they have degree 1. How many vertices are there in the graph? He is asking how many vertices are there in the graph. Very easy. See, let's assume there are let's assume how many vertices we have. So you see, we have already assumed that this is k. So total number of vertices we will have is k plus 1 plus 1 plus 2. So this is k plus 4. So this is the total number of vertices we have. Remember, this is the total number of vertices we have. K plus 4. This is the total number of vertices we have. Now we know number of edges will be equal to number of vertices minus 1. So number of edges will be k plus 3. Okay. So this is one equation we got. This is the one equation we got. Now you can apply the this formula, this handshaking lemma. So handshaking lemma says that summation of degrees. So 2 vertices of degree 4, so that means 2 into 4, that is 8, plus 3 into 1, that is 3, plus 2 into 1, that is 2, plus k into 1, that is k. So this is equal to twice the number of edges. What is number of edges? Number of edges is k plus 3. So this is equal to this. So finally you will get 13 plus k is equal to 2k plus 6. So from here you got k is equal to 7. You can see from here you got k equal to 7. So our answer will be 7 plus 4. Remember, our answer will be 7 plus 4, that is 11. So the answer will be 11. Okay. Let's see next question. Consider the graph shown below. This graph is. So let's see what is this graph. This is a complicated graph they have given. So what is the degree of this node? So the degree of this node is 4. The degree of this node is 4. the degree of this node is 4 and the degree of this vertex is 4. What is the degree of E? The degree of E is 1, 2, 3, 4, 5. The degree of E is 5. The degree of F is 1, 2, 3, 4, 5. So 5. This is, so you can see, first of all, this is not a complete graph. Why? Because in a complete graph, what happens in complete graph, all the vertices have the same degree. So this is not a complete graph. In a complete graph, all the vertices have the same degree. But here you can see some vertices have degree 4, some vertices have degree 5. So this is not a complete graph. Okay. Now, let's see, is this bipartite graph? Let's see if this, let's try to make it bipartite. Let's see. Actually, this is not a bipartite graph. There is a reason why. See, let's assume there is a theorem. Actually, we have a theorem. So let me tell you this theorem. So a graph, this is a theorem. This is an important theorem. So you can note down this theorem. A graph G is bipartite. A graph G is bipartite if and only if there is no odd cycle. So this is an important theorem. You can note down this theorem. A graph is bipartite if and only if there is no odd cycle. Means in the graph you should not have odd cycle. You should not have odd cycle. But in this graph you can see there is an odd cycle. A, B, F. This is the odd cycle. You can see A, B, F. So this is the odd cycle. So because we have odd cycle, so it is not a bipartite graph. So it is not a bipartite graph. It is not complete graph. Okay. Did you get this point? A graph is bipartite if and only if there is no odd cycle. But in this graph we have odd cycle, like ABF, this is the odd cycle, like DEC, this is the odd cycle, like AED, this is the odd cycle. So we have odd cycle, we have at least one odd cycle, so we can say that it is not a bipartite graph. So the remaining option is option C. Okay, so the answer will be Hamiltonian graph. You don't need to check it because it will take a lot of time. You don't need to check it. You can just directly answer that it is Hamiltonian graph. Okay, so you can try to find if there is a Hamiltonian circuit or not. For example, A to D you can go, from D to C you can go, from C to E you can go, from E to B you can go, from B to F you can go, and from F to A you can go. So this is your Hamiltonian circuit. You can say this is your Hamiltonian circuit. So this is Hamiltonian graph. Let's see next question. Consider the graph given below as which of the following graph is isomorphic to above graph. So this is the given graph and he is asking which of these graph is isomorphic to the given graph. Okay, so just you need to check. Okay, so he is saying that U1, U2, U3, U4. So remember, first thing you can see, this is a complete bipartite graph. You can see, you can notice this thing that this is a complete bipartite graph. So this is one partition, U1, U2, U3, U4. This is one partition, and another partition is U5, U6, U7, U8. So you can see these are the two partitions, and you can see this graph is actually complete bipartite graph because, so wait a second, this is not complete bipartite, but it is a bipartite graph. This is a bipartite graph, but it is not complete. Why it is not complete? Because this U5 is not connected to U4. So U5 is not connected to U4. Similarly, this U6 is not connected to U3. So this is how you can say that this is a bipartite graph, but it is not a complete bipartite. And in this graph you can see every vertex has degree 3. This has degree 3, degree 3, degree 3, and so on. So every vertex has degree 3. Also this is a bipartite graph. So let's see all these options. In all these options, let's see what is happening. So first you can answer, you can say that this is not, okay, wait a second. This is not correct. Why? Because you see this V5 has degree 4. This V5 has degree 4. Okay, but in our original graph, each vertex has degree 3. In our original graph, each vertex has degree 3. So you can say that answer A is not correct. Okay, you can say that answer B is also not correct because this V6 has degree 4. Okay, so this is also not correct. Next, answer D is also not correct because V6 has degree 4. So that's why the answer is option C. So this is your answer. Option C is the answer. Okay, this is how you can eliminate the options. when you are checking for isomorphism, then it is a good idea to eliminate the options. So you can eliminate option A, option B, option D, and the answer will be option C. Okay. So these are all the questions, and if anyone has any doubt, then you can ask right now. So Khushbu, isomorphic graph can have anything, that does not matter. Okay, I am saying that a bipartite graph cannot have odd cycle. Our theorem goes that a graph is bipartite if and only if there is no odd cycle. That was our theorem. Okay, in isomorphism is between two graphs. Isomorphism is not a property of one graph. Isomorphism is a property of two graphs. You have two graphs. Okay, I give you two graphs, G1, G2, and then I ask you whether they are isomorphic or not. Okay, but bipartite is property of one graph. I give you one graph, and then you can check whether that graph is bipartite or not. If I give you a graph, then if you want to check whether that graph is bipartite or not, then what you have to do? You just need to check whether there is an odd cycle or not, because a graph is bipartite if and only if there is no odd cycle, means there should be no odd cycle. Okay, if there is an odd cycle, then the graph is not a bipartite graph. Okay, so anyone has any other doubt? So these are your graph theory previous year questions. If anyone has any doubt, any other doubt, then you can ask. Anyone? No one? Sir, what is the condition to check isomorphism between two graphs? If you want to check isomorphism between two graphs, then actually we do not have any condition that you can use to efficiently check isomorphism between two graphs. It is a very hard problem actually. So we have a definition of isomorphism. The definition of isomorphism I have already covered. So have you watched the graph theory lectures? These three lectures I have covered graph theory 1, graph theory part 1, part 2. So in the three parts I have covered the complete graph theory. Have you watched those lectures, Neha? So in those lectures I have covered graph isomorphism. In those lectures I have covered this graph isomorphism. There I told that right now we do not have any condition which we can use to say whether two graphs are isomorphic or not. Okay, we can use the definition, and the definition says that if you have graph G, if you have the two graphs G1, G2, let's assume you have two graphs G1, G2, then two graphs G1, G2 are called isomorphic if and only if between the set of let's assume this is the set of vertices of G1, this is the set of vertices of G2, then between the set of vertices of G1 and set of vertices of G2, if you have a bijection which preserves the edges, means two vertices are connected here if and only if they are connected here, then if this type of bijection is existing, then you will say that your two graphs are isomorphic. So let me take this example. Okay, let me take example. So consider this. Let's assume this is your graph. Okay, consider this: A, B, C, D, and wait a second. So yeah, consider this graph. Okay, so now consider this another graph. So okay, wait a second. Let me take something else. So what you do? Yeah, take this. A, B, C, D. This is your graph. Okay, this is your G1, and you can take this G2, and this G2 is like this. The G2 is like this. G2 is A, B, C, and this D. We are connected like this. Okay, let's name it 1 2 3, 1 2 3 4. So you can see these two graphs are actually isomorphic, because you can use the definition here. The definition says that two graphs are isomorphic if and only if you have bijection between the set of vertices a, b, c, d, 1 2 3 4. You can see you can give this bijection. This bijection you can give. You can see this bijection is as preserving. You can see why, because this AB has edge if and only if 1 2 has edge. You can see this AB, there is edge between AB, so there is edge between 1 2. Similarly, you can see there is edge between CD, so there is edge between 3 4. You can see. So this is how you can, you actually don't have any condition. You have to use the definition of isomorphism. So that's why checking whether two given graph are isomorphic or not is a very hard problem, very hard problem. Okay, so many researchers are working on it. They are trying to find the efficient solution. They are trying to find some condition using which you can check isomorphism of two graph. But right now, at this moment, at this point of time, right now we do not have any such condition. You will have to use the definition. And you can watch our graph theory lectures, graph theory 1 2 3. There I have already discussed about graph isomorphism. I have also taken 2-3 examples, I think, and I have told you how to check graph isomorphism. Actually, to check graph isomorphism, you can do option elimination, like I did option elimination. You can see in this question I did option elimination. Why? Because in the original graph, each vertex was having degree 3. Each vertex has degree 3 in the original graph. Okay, but here you can see option A, option B, option D. In each of these options, you can see, for example, in option A, this vertex V5 has degree 4. In option B, V6 has degree 4. In option D, V6 has degree 4. So that's why I have eliminated option A, option B, option D. So the only choice that is remaining is option C. Okay, so the best method to check isomorphism is to eliminate options. And you can eliminate options using which properties you can use. For example, you can eliminate options using number of vertices. So let's assume you have two graphs G1 G2. Then if G1 G2 are isomorphic, then what should happen? Then number of vertices should be equal. Remember, number of vertices in G1 should be equal to number of vertices in G2, first of all. The second thing, number of edges in G1 should be equal to number of edges in G2. The third thing, the degree set of G1 should be equal to the degree set of G2. So for example, this we used in this question we used the degree set, because if you make the degree set of A, then you will get 4. In that degree set you will get inside that degree set you will get 4 also. But for the original graph, if you make the degree set, then that will only contain 3. So we used this degree to eliminate options. So Khushbu is saying, so in case of isomorphic, we just need to check number of vertices, number of edges, degree sequence, degree set, all these things you need to check. Okay, any other doubt? Anyone has any other doubt? Anyone? So let me know if you have any doubt. You can ask right now, or else we can. Sir, if the graph is planar, then it will satisfy. But if it satisfies, then we can't say it would be planar graph. So yeah, if the graph is planar, then yes, E will be less than equal to 3v minus 6. Yes, it is correct. But if it satisfies E less than equal to 3v minus 6, then we cannot say that it will be planar. So Khushbu, I'll have to check whether it is a two-way implication or not. I'll have to check this thing. So basically whether this is two-way implication, whether this is one-way implication or two-way implication. So this I will have to check. Okay, I will let you know. Any other doubt, anyone? So if there is no doubt, then we can close the session, because we have a class in the morning also. So if there is no doubt, then we can close the session, and if you have any doubt, then you can ask. Okay then everyone, thank you. So see you in the morning. In the morning we have next class, and in that class we will study the remaining topics of group theory. Okay, so some topics are remaining, those topics we will study in the morning class. Okay, so thank you, good night.